Exercise number 2 or assignment number 2, question number 5 asks us, an aircraft generates 130 decibels of noise at a distance of 100 feet. What distance would a worker need to be in order to be under the OSHA exposure standard? And we're going to use 85 for that. Okay, so let's think about that. That's the distance formula. We learned the distance formula, or at least we learned a rule about distance. The basic rule we learned is that for every time you double the distance from a noise source, you reduce the sound pressure level by 6 decibels. If you have the distance, you add 6 decibels to the sound pressure, okay, or the number of decibels. Okay, so we could literally, if we wanted to estimate this, we could literally just say, oh, at 130 decibels at 100 feet, at 200 it would be 124 decibels, at 400 it would be 118 decibels, and so on and so forth. And we might be able to get at least a rough idea of what distance that we would need to be. But a more expeditious way is to use the formula for the relationship between the sound pressure level of decibels and the distances that we're interested in. Okay, so here it is here, and I'm going to give it a try. So let's see if we can't get something to write on here. Okay. 96% of customers recommend the Hartford based on their claims experience.
This conference will now be recorded.
Okay, so let me see if I can't show the formula at the same time that I'm doing this. And we will try our calculation. Now, at this point, as with the other recordings, it might be good for you to stop at this point and see if you can't do the problem on your own. Okay, however, and then come back to this if you have an issue with it or something like that. So you get a chance to do actually try it as well. Okay, so let's say that we want to try and solve this now. So I'm going to call sound pressure level 1 and distance 1 the initial distances in sound pressure level, and number 2 is the one sound pressure level 2 is going to be our final noise level, and D2 is going to be our distance that we're looking for. So in this case, it's going to be 85 decibels is going to be our final sound pressure level that we're interested in. Our initial sound pressure level is 130 decibels plus 20 times the logarithm of the ratio of D1. D1 is our initial sound pressure level, which was 100 feet, over D2. That's what we're really solving for, the final distance that we need in order to achieve the sound pressure level we want. Okay, so let me move this up a little bit so we can see it. Oops. I'm gonna have to work around that, I guess. Okay, so let me work up here for a bit. So what do we have here? If I move 130 over to this side, okay, 130, it's going to be minus 45 is equal to 20 times the logarithm of 100 over D2. Okay, divide by 20, and we wind up with negative 2.25 times the logarithm of 100 over D2. Okay, so now I need to get this side of the equation out of that logarithm. Okay, and in order to do that, I have to take the anti-log of both sides. When I take the anti-log of a logarithm, it's just the value itself. So in other words, the log of A, the anti-log of log of A is A. If I have a value like A, the anti-log of that value is 10 to the A power. Not minus A, but 10 to the A power. So in this case, if I take the anti-log, this is going to be it's going to be 10 to the minus 2.25, right? Just bringing that number up to the exponent for 10 is equal to 100 over D2. Okay, I think this anti-log business comes up in a couple of these problems. So it's good to kind of get a focus on it now. Okay, so I can cross multiply. I can just put that over 1 and cross multiply. So D2 times 10 to the minus 2.25 is equal to 100 times 1, or 100. So D2 is going to be equal to 100 divided by, bring that over to the other side, 10 to the minus 2.25. Just simple algebra. So let's take out our calculator and see what we come out with. Okay. So if I can't get it into the front, here we go. Okay, so let's see. First, I'm going to take 2.25, 2.25. I'm going to make sure it's a negative 2.25. And I'm going to take that, I'm going to use that as the exponent of 10. Whoops, I did that twice. Let me try it again. Clear it. 2.25. And that's 10 to the negative 2.25. That's the value. Now I'm going to clear out memory over here, and I'm going to put that into memory so I have it available for me. I'm going to clear that. Okay, so now I am going to finish this calculation. I'm going to say 100 divided by what I've just calculated. I'm going to pull that out of memory, and I'm going to divide by that. And it comes out to 782 or 83 feet. So that would be my final result on this problem. Let me just write that down. So D2 is equal to 1778. I'm going to round it for our purposes to 3 feet. Okay, so just for the argument's sake, let's just take a look at this. 130 at 100 feet. If we double the distance to 200, it would be 124. If I double the distance to 400, it's going to be 118. If I double the distance to 800, it's going to be 112. Double the distance to 1600, it's going to be 106. Double the distance 3,200 feet, it's going to be 100. Double the distance 6,400 feet, it's going to be 94 decibels. Double the distance to 12,800 feet, it's going to be 88 decibels. Not even quite far enough, right? Okay, and then finally, let's see, double the distance finally to 25,600 feet is going to be 82 decibels. So we don't really, it doesn't really work for us. It's not going to be an even number of decibels for us here. So the formula was really the best way for us to go, but at least we can confirm that it's between 12,800 and 25,000. Kind of a little check on the work that we did. Okay, we'll move on to the next problem.
This conference will now be recorded.
Okay, so next problem in assignment number 2, question number 6. The root mean squared pressure level from a sound source is 40,000 micropascals. What is the sound pressure level of this source? In other words, how many decibels is the source is what we're asking here. So we have a measurement, sound pressure level in decibels. We have a formula for that. Sound pressure level is equal to 10 times the logarithm of P1, the pressure 1 over pressure 0. Pressure 0 is the reference pressure squared. That resolves down to, because it's a square and a logarithm, that resolves down to 20 times the log of P1 over P0, the reference pressure. So all we need here is sound pressure level is equal to 20 times the log of pressure 1 over the reference pressure, the pressure we want over the reference pressure. Now, the main thing here is we want to make sure that we're working with the same units. In other words, is it dynes, or is it newtons per meter squared? In this case, we're working with micropascals. So 20 micropascals is the reference level. So this is going to be a 20. So let's pull up a sheet of paper and let's see if we can't work this out. Okay, and so sound pressure level is equal to 20 times the log of the pressure that we're working with, which was 40,000 micropascals over 20 micropascals. So notice it's unitless, right? You lose those units, they cancel out. It's unitless, so it's 20 times the logarithm of, let's see, 40,000, 2,000, 2,000. I believe that's 2,000. Yes, it's 2,000. Okay, so now let's see if we can't resolve that with a calculator. Okay, so I'm going to clear everything, and I'm going to say, let's get our logarithm first, 2,000. Okay, the logarithm of 2,000 is 3.30, and we're going to multiply that by 20. And the sound pressure level is 66 decibels. Okay, get my pen again. 66 decibels. Okay, that one's pretty simple, I think, right? That one was the least straightforward. We didn't have to do multiple calculations. Okay.
This conference will now be recorded.
Okay, moving on to question 7 on assignment number 2. Workers cleaning or repairing equipment in HVAC room for an entire day. The 3 identical compressors are running. You conducted a noise survey last year and found that the levels above the threshold limit value, dose is equal to 1.72. Calculate the new dose if you shut down one of the compressors. Okay, I think probably the simplest way to look at this is to consider that each one of these machines is contributing equally. Let me just get back to the pointer. Each one of these machines is contributing equally to that dose of 1.72. Each one of them is contributing 1/3 of the energy that he's being exposed to. So if we shut down one of the machines, then simply the new dose is going to be equal to 1.72 times 2/3. Okay, and let me pull up my calculator. Oops. Here we go. Okay, 1.72 divided by 0.6667, or time, whoops, excuse me, 1.72 times 0.6667. Okay, comes out, oops, I seem to be having a little problem with my fingers here at 1.72. See if this works now. Be 1.14, 1.15 would be the new dose if we shut down one of the machines. And similarly, if we shut down 2, we would reduce it to 1/3 of the initial dose. Okay, you could also take a look at it from the perspective of TLV means that you're using the ACGIH standard, which is 3 decibel noise reduction, doubling rate, and you could look at it from in terms of what the individual dosage is. The dose over a whole day is how much that's been reduced by reducing the overall sound pressure level, or perhaps use the OSHA standard. Okay, in that case, I would have had to tell you whether to use OSHA or NIOSH. Okay, so hopefully that's simple enough that I think we can move on from there.
This conference will now be recorded.
Okay, moving on to assignment number 2, question number 8. Calculate the permissible exposure limit in minutes for a constant 98 decibel noise source. Okay, a couple of keys here. One is that we're talking about the OSHA exposure period, and we're talking about 98 decibels. We do have a formula for calculating the exposure duration. Okay, and this is the time in hours. We have the table, of course, that you can use. And OSHA uses a 5 decibel exchange rate, and the starting point is 90 decibels. If we had said NIOSH or TLV or ACGIH TLV, we'd be using a 3 decibel exchange rate with a starting sound level of 85 decibels. Formula is going to look a little bit different. Same formula, just the 85 and the 3 are exchanged for a 90 and a 5 here. Okay, so let's go ahead and do this calculation. We want to know how long he can be exposed to with at 98 decibels. So we're going to calculate for the number of hours at that sound pressure level. Okay, let's get a piece of paper to work with. And let's see. Okay, so time in hours, right? I'm doing this in hours, is equal to 8 over 2 to the sound pressure level, 98, not minus 90 is 8 over 5. Okay, we want to figure out what that's equal to. So we'll get our calculator out. Okay, first thing I'm going to resolve is 2 to the 8 over 5. I like using Excel for that, but as it happens, I have a function here on my calculator to allow me to do that. This is the x to the y power. So the way that works is we're going to find out the, we're going to take 2 to the 8/5. Okay, first thing I'm going to do is I'm going to figure out what 8/5 is. 8 divided by 5 is equal to 1.6. I'm going to put that into memory. Okay, I'm going to clear that out. And I'm going to say, okay, so we want to take that number. We're going to want to take 2. First, I'll put in 2. Click on x to the y value. It's going to use the 2 as the x that's in the register already. I'm going to recall my 8/5. And then I'm going to say, what is that equal to then? So 2 to the 8/5 is equal to 3.03. So that does make sense, right? Because 2, it's less, 2 to the 1 would be 2, 2 to the 2, and this is would be 4. So it's between 2 and 4. It's always nice to kind of make a judgment as to whether you are on the right track or not. Okay, so now I'm going to clear out what was in memory before, and I'm going to put this into memory and clear it out. I'm going to take 8, and I'm going to divide it by that fraction. So let's see, recall memory. And that gives us 2.639 hours. Now we were asked to answer the question in minutes, so we just simply multiply by 60 to get the minutes. Okay, and it's 158.34 minutes. Okay, and I'll just write that in case you can't hear me. For some reason, there's a sound problem or something like that, 158. Okie doke.
This conference will now be recorded.
Okay, moving on to problem assignment number 2, problem number 9. The maximum noise reduction rate for earmuffs is 31 decibels. Calculate the maximum 8-hour sound level a worker can be exposed to using the ACGIH TLV. Okay, let's think about this. The ACGIH TLV is 85 decibels, right? You can be exposed for 8 hours at 85 decibels. So we need to know what the level of noise is that will reduce the worker's exposure from that noise level down to 85 decibels. Okay, and since he'll be exposed at 85 decibels, he can work for 8 hours. But we have to know what is the maximum level of sound that he can be exposed to, so that those headphones, those earmuffs, will achieve that amount of noise reduction. So NRR is equal to the 31 minus 7, right? Oh, I'm sorry, the attenuation, the decibels. The amount of attenuation we get, the decibels, is equal to 31 minus 7 over, let's see, and we divide that by 2. So that's the NRR is equal to the let me rewrite this just to make this a little bit clearer. The amount of attenuation, the number of decibels of reduction that we get, is equal to the NRR minus 7. We take the 31, subtract 7, and then we divide it by 2. Okay, so if we actually go ahead and do the math here, the number of decibels of reduction that we can get is 31 minus 7 over 2. Okay, so if we do the math there, and let me get my calculator, clear everything out here. If I do the math there, that's going to be 31 minus 7 is 24, divided by 2 is 12. I guess I don't really need that, is equal to 12. So the attenuation that I can potentially get from these earmuffs is equal to 12 decibels. Since we can't afford to have the worker exposed above 85 decibels. If we want him to work for 8 hours, we just add that 12, and the loudest noise that he can be exposed to during that period is 97 decibels. Okay, that's the loudest that environment can be over 8 hours, given that he's wearing the earmuffs, and his actual exposure is reduced to 85 decibels.
This conference will now be recorded.
Okay, assignment number 2, question number 10, the final question. An industrial machine located on the factory floor is generating sound at a power level of 112 decibels. Okay, that's the machine itself. That's the amount of energy or the amount of power that's coming out of the machine. It's located in the corner. That's going to be significant to us because as this energy is coming out, the sound pressure is coming out from this device, it's concentrated into half of a hemisphere, into a quarter of a sphere. So now that gives us a picture of how it's being diluted as the distance is being increased. What is the estimated sound pressure level at a distance of 20 feet? So we have a formula for this. This is a relationship between the sound pressure level and the sound power level. Okay, sound power level, that is our 112 decibels, right, is equal to the sound pressure is equal to, the sound pressure level, right, is equal to the sound power level, right? That's our power level in here. That's our 112 decibels minus 20 times the logarithm r, that takes into account the distance from the source, minus 0.5, a correction factor, plus a correction factor for temperature and pressure. We're not going to bother with that, where it's a factory of normal temperature and pressures, nothing dramatic. Okay, plus a directivity index. In other words, something that accounts for whether this is standing in the middle of a room, or it's against a wall, or in this case, it's in a corner. So I'm going to start to put that formula together. Let me get a piece of paper. Okay. So the sound pressure level, which is what we're after, number of decibels, LP, I'll use LP instead of sound pressure level, is equal to 112 minus 20 times the logarithm of the distance. I don't remember what that was. Let me get this. Where is it? Down here. 110, it's in the corner. Distance of 20 feet. And let me bring this back. Minus 20 log of 20 feet. 20, we're using feet, we're using English units all the way through here, plus DI. Now I'm going to have to calculate DI. So let's figure out how to calculate that. If I go back to this other slide. Okay, so here is our situation. Here are machines in the corner. And I don't know if I can expand that a little bit. Tough for me to see. I'm sure it's impossible for you to see. Okay, Q for this setup, for this spherical radiation, okay, 1/8 of a sphere radiation is equal to 8. DI is equal to 10 times the logarithm of that Q, or 8, 10 times log 8. That's 10 times the logarithm of 8. Okay, let's see if we can't resolve this now. LP is equal to 112 minus 20 times the logarithm 20. And get our calculator here. 20. I'm going to turn my pointer off here, my pen off. 20. Oops, hang on a second here. There we go, 20. Find the logarithm of 20. That's the logarithm of 20 multiplied up by 20. And that's equal to 26.02. I'm going to put that into memory. 26.02. I'm just going to put 26 down there for us. Okay, I have to keep switching back between pen and pointer. 26 plus 10 times the log of 8. Okay, now I have to go back to my pointer and see. Okay, 8. Logarithm of 8. Whoops. 8. Logarithm of 8 is this. Okay, times 10 is equal to 9.03. 9.03. Okay, and you'll notice that we're subtracting for the distance, right? Because as we're getting more distant, sound is getting lower, but we're adding for the fact that it's more direct, the sound is more directed. Okay, so I'm going to go back up to my calculator. Let's see, 20 times the logarithm of 20, 20. Find the logarithm of that, multiply by 20 is equal to this, 26.02. Okay, so I need to subtract that from what I have in memory. So let's see. I am going to change the sign on this. And I'm going to say plus. Oh, I hope I didn't change something there. Did I change the sign on that? Okay. Plus, recall memory, equals 95. Oh, it should be 95 decibels. I guess it was closer than I thought. Oh, I know what I forgot. Do you guys, can one of you guys tell me what I forgot? Let's go back to the formula and it'll be obvious. Where is that formula? There it is. What did I forget? I forgot to subtract 0.05. So the correct answer is minus 0.05, right? Is going to be 94.5 decibels. There we go. Okay, I knew I knew something was wrong there. Okay, it's 94.5 decibels. All right, so that concludes this homework. I hope this helps. I hope that the way you use it is that you look at you get to get a look at how I start the problem, how I approach the problem. You go and try it for yourself, and then you come back and check your solution. Okay, so good luck on the homework. Bye.